Good morning. My name's Danny Williams, and I'm going to be helping to host today's webinar on FANS 101. For those of you who have joined us today, I wanted to give you an update that if you aren't already, please make sure that you're connected to a laptop PC of some sort so that you can watch what we're going to be displaying today and talking about. And it's also very important that you keep your volume on your machine on, because that's how you'll be able to hear what we're going to be discussing today. Also keep in mind that our webinar today is going to be recorded, so we will be sending out a recording of today's webinar afterwards, and it'll also be available on our YouTube page. We're also going to be accepting questions throughout today's webinar, so if you do have any, please submit them to our the questions essentially section on the interface you guys have, and we'll be sure to address those at the end. For those of you who joined in as I started talking, just a reminder to be connected to a PC so that you can see and listen in on what today's webinar is going to be. I'll be sure to give you guys about 60 to 90 seconds if you need to make that adjustment. Alrighty, and we'll go ahead and get started. Also a reminder again that today's webinar will be recorded, so no worries if you need to head off. You'll be sure to get this later today or tomorrow.
Thank you and welcome to FANS 101, an introduction to fans and electronics cooling applications, where we will discuss the fans and blowers that are typical in the industry. The topics that we will cover will be from a system integrated perspective rather than that of fan blade design. Specific topics we will discuss include fan basics such as performance curves, fan or affinity laws, and flow characteristics. After introducing some basics, I'll turn it over to Dr. Raghupati to discuss how fans are characterized experimentally. We will then discuss how fans are simulated. Electronics thermal design software such as FloTHERM and FloTHERM XT, fans and blowers can be included in the analysis via a black box approach. We'll provide an overview of this approach along with some pros and cons of this method. FloTHERM XT is able to simulate the rotation of blade geometry. In some situations, it is necessary or advised to model fans or blowers with this approach. Along with an introduction to this technology, we'll discuss when this would be the recommended approach. We will finish with an example developed in FloTHERM XT of a graphics card with an integrated blower. Fans or air movers can be grouped into two categories. The first category is axial. I've shown two examples, one a drone and two a workhorse in the electronics industry, the axial fan. These fans are termed as axial because the flow enters and leaves the fan along the axis of rotation. The axis of rotation is identified with the red dashed line. The blue arrows indicate the bulk airflow direction. The second category is radial or centrifugal. We'll see later that air movers of this type are known by many different names. The two examples shown are a centrifugal blower in the upper right and a motorized impeller. The blower image is a cross-section view and isn't showing the inlet. Fans of the radial type have flow that enters or leaves, or both, in a radial direction from the axis of rotation. From a system integrated point of view, one of the most important characteristics of a fan is the performance curve. Let's start by looking at a typical performance curve for an axial fan. Axial fans typically have the shape shown. In the center of a curve, there's a stall region, which for our purposes represents an area where you don't want your fan to operate. Ideally, the fan operates in the system in the lower area of the curve, delivering more flow at a lower static pressure. Dr. Raghupati will discuss the fan curve in more detail while introducing us to fan testing. If we plot a curve from a radial blower with about the same dimensions as the axial fan, we can see that it can provide airflow at a higher static pressure, but in systems that have low flow resistance may not provide as much flow as the axial fan. We can also see that it has much more consistent pressure versus volume flow rate characteristics. The last fan or blower we'll look at is the centrifugal blower. The curve has the same shape as a radial fan, but with a lower maximum static pressure and maximum volume flow rate. The centrifugal blower is essentially a radial fan placed in a confined duct, so it seems reasonable that there will be some performance losses before the flow exits. So why would you choose one fan over another? There are a number of considerations including the fan curve, but another is form factor. Incorporating a fan into a system may require the integrator or engineer to match the form factor of the system with the design of the air mover. Integrating fans into systems is a full topic in itself and we will discuss in a future webinar. An important part of integrating a fan into a system is understanding how the fan performance changes with RPM or with air density. These relationships are known as fan or affinity laws. I've included 3 fan laws that are useful for our discussion. The first equation shows the fan volume flow rate scales linearly with fan RPM. The second equation shows that the fan static pressure scales with RPM squared and linearly with air density. The last equation shows that the power associated with the fan scales with RPM cubed and linearly with density. If we look at a typical blower curve at an RPM of RPM 1 and an elevation of sea level, and compare it to the same blower at a reduced RPM, we can see how the performance curve changes. Electronics thermal design software such as FloTHERM or FloTHERM XT is able to use these relationships to assist the designer in creating control schemes for balancing thermal requirements with power requirements. It allows for systems to be designed that adjust fan RPM to provide only the necessary airflow and as a result lower the power requirements of the cooling system. If we plot the same blower at RPM 1 but at an elevation of 4,000 meters, we can see the effect of the density change on fan performance. Looking at the plot, we see that the maximum volume flow rate of the blower doesn't change with elevation. The effect of the elevation gain is that the fan will deliver less mass flow because of the lower density. We remember from thermodynamics that the temperature rise of the system is directly related to the mass flow rate. At a higher elevation, more volume flow will be required to maintain the same mass flow rate. This is leading to a topic that deserves more time than we have now, so I'll end it there and say this will be covered in the future in more depth. This brings us to fan testing. I'll now invite Dr. Gupati to discuss how fans are tested.
Thank you, John. At Electronic Cooling Solutions, we have been testing many different types of air movers over the years. This is a short summary of fan test procedures using the American National Standards Institute and Air Movement and Control Association International 210 standard. The information in the next few slides is by no means comprehensive, and listeners are strongly recommended to look into additional material for more comprehensive information or get back to us with specific questions. The primary purpose of fan testing is to understand the performance of the fan in terms of the static pressure head it generates at various airflow conditions. It is basically deriving a curve as shown in the figure on the right. The curve represents the performance of the fan at a particular speed. The two most important points for performance definition are the maximum static pressure generated by the fan at zero airflow condition and the maximum airflow at free delivery. Although these points are used to define the performance of the fan, the most useful information is the nature of the curve in the region of the operating point of the system in which the fan is used. The figure also shows the sweet spot for operating the fan at its maximum efficiency region and the stall region that should be avoided. During fan testing, a number of points over the entire airflow range are tested to ensure capturing the behavior of the fan over these various conditions. While the nature of the curve may vary between the different types of air movers, the test methodology remains fairly similar. It is important to identify the maximum airflow at free delivery. This is similar to a fan that is placed in a room with no obstacles upstream as well as downstream of it. The maximum stagnation condition static pressure is identified by creating a zero airflow through the fan while the fan spins at the set speed. Additional points are created by varying airflow through the fan and identifying the static pressure generated by the fan. While performing fan tests, it is critical to record input into the fan, namely voltage and current. If it has PWM control, it is important to set it correctly and record the input. Also, it is important to record speed of the fan by using a strobe, a tachometer, or by tapping into the tach wire out of the fan. Since airflow is measured across a calibrated nozzle in this methodology, it is important to accurately measure temperature of the airflow across the nozzle, the barometric pressure corresponding to altitude, and the relative humidity. All of these affect the density of the air. Relative humidity has a second-order effect on the density of air, as humid air is less dense than dry air. The pictures show the schematic of fan test equipment used and configurations for fans blowing into the chamber and sucking air out of the chamber. The chamber has a centrifugal blower to allow variable exhaust. There are settling mesh elements before and after the nozzle plate to make the flow as straight as possible. Pressure at each cross-section is measured by multiple static pressure ports connected by a tube. This averages fluctuations measured at a cross-section. Static pressure is measured at sections shown as PL7. Differential pressure across the nozzle is taken at sections PL5 and PL6. The Bernoulli's equation coupled with continuity equation is used to compute the airflow that passes through the nozzle. This is easily calculated using the Excel sheet that is provided along with the airflow chambers. During fan testing, either of the configurations can be used. Let's consider the scenario where a fan is attached to the chamber and is blowing inside. In this case, the configurations of the manometers is as shown in the bottom right figure. Static pressure probe is connected to the port marked with a positive sign. The P1 and P2 are connected to the positive and negative signs respectively. For free delivery condition, which is one extreme of the PQ curve, the fan is set at a speed which needs to be characterized. The variable centrifugal blower on the other end of the chamber is adjusted so that the static pressure probe reads 0. It is necessary to use the centrifugal blower to overcome the impedance caused by the air passing through the nozzle plate and the settling mesh screens in order to create a zero static pressure condition. For the other end of the PQ curve, which is the stagnation pressure condition with zero airflow, without changing the speed of the fan, the nozzle plates are closed completely so that no airflow goes across the nozzle plate. We have found that this is the most reliable way in order to create a zero flow across the nozzle plate. At this condition, it is important to make sure there are no leaks in the system. The static pressure can be read off the manometer used for static pressure measurement. There is no use of the differential pressure manometer in this case. In fact, it is recommended to remove the tubes from the ports to avoid the manometer liquid gushing out. Additional points on the middle of the curve are generated by setting a specific airflow using the assistance of the variable exhaust system. The next couple of slides shows the examples of actual setups and equipment. A sample nozzle plate is shown in the figure on the left. It shows nozzles ranging from 0.688 inches to 2 inches. Each nozzle is valid within a flow range where it is calibrated for, and it should be used only within that calibrated range. It is okay to use combination of nozzles for higher flows than what a single nozzle is calibrated for. The middle picture shows a complete setup of a high-pressure fan being tested. In this case, a special steel faceplate was fabricated to withstand the high pressures generated by the fan during the measurement of points closer to the stagnation point. The setup also shows a power supply powering the fan and wiring for the pulse width modulated control and tachometer readings. The variable centrifugal can be seen on the far end of the picture for providing assistance in setting the required airflow values. For measurement of airflow in small quantities, it is important to use nozzles that are very small. At Electronic Cooling Solutions, we have nozzles ranging from 0.125 inches, which are capable of measuring 0.1 CFM, all the way to 3 by 6 inches, which are capable of measuring 4000 CFM. During low airflow measurements, it is also important to use micromanometers as shown in the figure on the right. It can measure pressure at 0.001 inch increments. Fan performance testing is not necessarily done only on standalone fans. It is sometimes done on fan trays either with parallel fans or fans in series. It is also done to get performance data on combination with or without airflow straighteners as shown in these pictures. The resulting measured performance curve can be used as input into the simulation directly. This is also applicable for fans that have grills or finger guards. The picture shows a prototype fan tray being tested with a honeycomb airflow straightener that is placed in between a series setup of fans. The honeycomb can be seen in the far right picture. The actual setup in which the performance curve is characterized is also shown in the top right figure. With this, I would like to complete the section on fan testing and would like to hand it over back to John. Thank you.
Thanks, Arun. Very useful information for us to understand. We've talked a little about how if the air moves axially or radially from a fan, it may influence the decision for use in a design. We have also looked at fan curves and how they are experimentally determined. I'd like to next look at the exit flow characteristics of the various air movers before we discuss the different modeling methodologies. I've also included the numerous names I've heard used for each of the types shown. The only consistent name I've heard is axial fan to describe an axial fan. The blower exit velocity can look quite different depending on the design of the blower and size of the duct. The flow may be biased to one side or exit at an angle. Axial fans typically have a tangential component or swirl velocity exiting the fan. The amount of swirl can change depending on the operating point of the fan. The radial fan tends to have a radial component to the exit velocity, but I suspect that the exact profile depends on the blade design. That leads us to fan modeling, starting with the black box approach. One aspect of this approach is to capture some of the characteristics of the exit velocity in addition to the geometric and fan performance characteristics. The benefit is a low computational cost and takes advantage of all the information that is typically available to a system integrator. The images shown are taken from FloTHERM XT using the centrifugal fan, and radial fan smart parts and give you an idea of what the exit velocity looks like. If we look at the property sheet of the centrifugal fan as an example, we can understand the type of information that is used to develop the model. I'll discuss a few key areas. The first area pertains to the physical dimensions. This particular model builds the model of the exit duct and allows for more inputs. The next area is fan derating, or RPM derating. I say RPM so we know I'm talking about angular velocity of the fan, realizing some prefer to work in radians per second. Fan derating is the ratio of the current RPM to the RPM that the fan curve is based on. This derating, combined with fan laws, will scale the performance of the fan. The next input area is fan curve. Typically, fan models allow the user to use a fixed volume flow rate, or a linear fan curve. The only inputs are the maximum volume flow and the static pressure, or in this case, a nonlinear fan curve, and is typically used in fan models of this sort. The last setting is thermal power. The software will let the user define a thermal power dissipation associated with the fan. There are a number of other inputs that may be available. RPM, or angular velocity. In the case of axial fan with swirl or the radial fan, the user can specify the RPM, or radians per second, to allow the software to provide a directional velocity component. For axial fans, there may be an option to specify the exit velocity direction. The options are typically angled, swirl, or normal. The angled option would be chosen if there was a vent or baffle turning the flow. Rather than model the vent explicitly, the fan model can direct the flow at the exit angle. Fan failure is an option to essentially turn the fan off. This is useful if you want to study the effect of fan failure, not only the reduced flow in the system, but also that there is an additional opening that could allow air to recirculate. There also may be an option to include fan noise. The software will scale that noise based on the derating factor. Flow resistance. It may be possible to associate an additional flow resistance to a fan to capture the effect of a finger guard, for instance. Transient RPM control. The last option I'll discuss has to do with something I touched on earlier. In a transient analysis, this option would allow the fan speed to be controlled by a component temperature. If the temperature rises, the fan speed will increase. This linking would allow the engineer to develop a control scheme to maintain component temperatures at the appropriate fan speed. This is an interesting feature that will be discussed in more depth in the future. In FloTHERM XT, there is an additional option when modeling fans. FloTHERM XT can simulate the rotating geometry. There are two options available for rotating geometry, each with strengths and requirements that we will discuss. The first option is rotating reference frame. The analysis can be steady state or transient. The rotating geometry must be periodic. This isn't a strict requirement, but strongly advised for this approach, and it will become clearer in the next few slides. The stator geometry must be axisymmetric. The flow must enter along the axis of rotation. Generally, the flow enters along the axis of rotation and leaves all other faces. It is possible that the flow enters radially and exits along the axis of rotation and is supported by this method. It isn't typical in electronics cooling applications, though. The second option is sliding. With this option, the mesh moves with the rotating geometry. Transient only. Because the mesh is moving with respect to time, directly related to the rotation speed of the geometry, a transient analysis is a requirement. An advantage is that the method supports rotating arbitrary geometry with any entry and exit points. Either method, the rotating reference frame or sliding, uses a rotating region to identify the axis of rotation and the geometry to be rotated. The region must be a revolved body like a cylinder with the axis of rotation aligned with the rotation axis of the geometry to be rotated. Let's discuss how the rotating reference frame approach works. In this approach, the rotating region is sliced into rings of equal width. In the rotating region, flow parameters are calculated in the local rotating coordinate system. Values of flow parameters are circumferentially averaged over each of the rings and transferred as boundary conditions to the stationary reference frame. If flow enters and leaves along the same boundary, the averaging approach would not be accurate, and in this case, the sliding approach is recommended. The sliding approach requires less explanation in that there are fewer assumptions. The upper left image shows a cartoon of the mesh at time equals 0. The image below that shows the mesh at some later time. The image on the right shows the analysis of a blower in FloTHERM XT, where you can see that the mesh in the rotating region has rotated. We'll finish up with a quick example from FloTHERM XT of a graphics card using the rotating reference frame approach. The first step will be to create geometry that will become the rotating region. If you look at the image in the upper left, you'll notice that I've kept the boundary of the rotating region some distance away from the boundary of the graphics card cover, which will result in a more uniform flow condition at the boundary of the rotating region. At the modeling level in FloTHERM XT, I have chosen rotating region with averaging. The next step is to attach the rotating region non-geometric smart part to the cylindrical body. To attach, you just drag and drop the smart part to the cylinder. With the construction dialog, I specify the angular velocity of 5,000 RPM. I also choose the static base within this region, shown highlighted in the lower left image. The last step I take is to specify a local mesh size of 2 millimeters in the rotating region. Let's take a look at some results to point out some of the recommendations. This image is showing a contour plot of fluid temperature with velocity vectors. This graphics card with the integrated blower is a great example of when modeling the rotation rather than with the performance curve is important. Anytime there is geometry near the fan or blower, the performance curve doesn't represent the flow situation. With a detailed approach, I can develop a much more accurate model and ultimately a better design. The next plot shows a speed contour with a computational grid. The grid is fairly coarse for this type of analysis, and a minimum of 2 to 3 grid cells are recommended between the rotating region boundary and immovable stationary bodies and between the end of the rotor blades. Though the grid is coarse, I would like you to notice how well the geometry is resolved, particularly the blades, with the smart cell technique used by FloTHERM XT. Even the curvature of the graphics card cover is captured well with no additional grid settings or higher mesh count. This model has about 580,000 grid cells. We'll end with flow animation. It does appear that the heatsink fins are too close to the blower to properly distribute the flow. Perhaps in a future webinar, I will optimize this blower heatsink combination and share the results and methods used. That concludes the topics we set out to cover. Thank you very much for attending. I also want to thank Dr. Raghupati and Electronics Cooling Solutions for discussing how fans are experimentally characterized. Lastly, I would like to point out there's much more to cover when discussing fans for electronics cooling applications, and hope you will join us again when we dig deeper into fans.
All right. Thank you everybody for attending today. And while we were watching this, we did get a couple questions come through. So to help me answer those today, we have Richard Ozaki, who is one of our application engineers and resources for all things related to mechanical modeling and simulation, things like that. So Richard, are you there?
Hey, Danny, yes, I'm here.
All right. So one of our first questions we got, if you can help us, is can you comment on fan dust fouling?
Yes, yeah. So if you start to see dust buildup on your fan blades, that could be potentially a problem. If because the fan is obviously moving, the dust particles are going to be smaller than the boundary layer thickness. But I'd be more concerned about parts downstream of that fan that are getting blocked, things like filters, heat sinks. The fan itself, the actual dust buildup isn't too much of a problem until it gets to the bearings. But yeah, it's indicative of a problem downstream.
Okay, gotcha. And then the second question we have is how are filters modeled?
Filters, yep, sure. So if you are pulling air through a system, then you do need to have filters to stop dust ingress, ideally. So you would model a filter with like a porous media. So you would set a pressure loss versus approach velocity curve, and then there would be a pressure loss across that filter.
Okay, gotcha. And then the last question we have today is which is better, a push or pull through system for a server?
Okay, that's an interesting one. So they both have pros and cons. I would say most servers on the market are actually push. Okay, so you have fans at the front to push air through the server, or maybe a combination of push and pull. The reason you typically want to push air through a system is that it actually pressurizes the server, right? So the pressure on the inside is higher than the outside. That means that you get leakage going outwards or out of the server rather than pulling air into the server if you have a negative pressure. So there's pros and cons to both, but I would say, typically you're going to want to pressurize the system slightly above ambient rather than below.
Okay, gotcha. Well, that was the last question we have today. But however, if anybody in this call still has a question in the upcoming days, please feel free to give the number on your screen a call or shoot us an email, and we'll be happy to help you in any way that we can. Thank you very much for helping us today, Richard, and everybody will receive a recording notification via email either today or tomorrow. And we hope to see you again soon.